My name is Suklesh, and today I'm going to be presenting about response time analysis by in hierarchical scheduled time partitioned distributed systems. Now, upon hearing this name, it might be a little bit confusing and overwhelming, but I'll make sure that it's much more easier so that you can understand. Now, as an introduction, let us think that we are an airport employee and we are assigned to build an aircraft. There are many aspects in which we need to build the aircraft. Let's focus on one aspect, that is electrical and software integration of the aircraft. Now, when we do this, what we notice is that nowadays there are integration between the software and the hardware, but during the modernization of the aircrafts, because they were manufacturers from different places, it was tough to get everything into a standard form and integrate it with each another, because integration is the key, and without that, flight or any other means of aviation is going to have problems. Now, when the integration is done, it motivated the development of standards of integrating several software components into the same computer, reducing the amount of hardware. So there was more software than hardware, and this is also true nowadays, where some airlines have more computers and there's more software integration over there than hardware integrations. So this is actually a very useful thing which was done. To guarantee the integrity of the system, these standards specify partitioning of time and space in such a way that a particular component is assigned a portion of hardware resources and portions of the available computation time. This allows a separate analysis of different components and guarantees that there are no interactions among them that could compromise the integrity of the system. If there are compromises and there are interferences between the different components of the system, then and especially in something like a flight, it's going to be catastrophic in nature. Basically, I found that doing this application is so useful for avionics, and not only this, makes it much more easier to explain the topic using this as a tool. In this, what we need to know is one thing, that is the ARINC. The ARINC is basically the Avionics Application Standard Software Interface. It is a software specification for space and time partitioning in safety critical avionics real-time operating systems, that is RTOS. It allows hosting of multiple applications of different software levels on the same hardware in context of integrated modular avionics. As we see here, basically it helps in getting the avionics related RTOS. We have RTOS obviously on planes, and this basically helps in integrating all of those things together. The interesting part of here is that we also have a scheduler over here. So there are two types of schedulers in this case, and one scheduler is for assigning the different time intervals, and the other one is to dispatch the different tasks. The presentation describes a method for performing response time analysis in complex time partition distributed systems. And for processes, we focus on the ARINC 653 partitions using operating systems that are capable for concurrently executing set of threads inside each partition. Because in RTOSs of the aviation, we need an OS which can concurrently run everything together. It has to be powerful enough to do many tasks together. So if you see this, the presentation studies the analysis of hierarchically scheduled partition systems in which global partitioning policy is specified as a specific set of arbitrary time windows. So here we have different time windows which we are going to see later on. Now let us go to the partitioning system model. The system model is established for the analysis in time partitioned scheduling is based on ARINC platform, which we saw earlier, which offers a number of protected time frames called as partitions in which real-time tasks can execute. This is very similar to what we are studying. We have particular time frames, and particular instances can use the resource at scheduled time. This can be based on priority or the deadline. This is how it is used in the ARINC of avionics. Each partition can contain one or more time windows, like I said before, that define intervals during which the task of the partition may execute. The schedule of all the partition windows is specified for an interval that is called as the major frame. This is simply like how we use time frames for computer science. This schedule is repeated in a cyclic manner. Each window is specified by its start time relative to the start of the major frame, a duration, and the identifier of the partition. For a partition PK, so we have basically three things. That is a major frame, a duration, and an identifier for the partition. In this case, we have one thing, that is the task model is based on the end-to-end flows. Yeah, you see here we have something called as end-to-end flow. So also called as transactions over here. They are that are released by stream of periodic workload events. Yeah, so the E2E flow is basically transactions which happen. The tasks of the E2E flow execute one instance, like how we call job over here in computer science, we also use it over there. Per workload is event received, and therefore each task executes at an infinite stream of jobs, one for each period or event activating the task. These jobs are released with a relative time called as offset. So same thing is there in computer science, where we have an offset, and once this offset is met, we have to release whatever resource it is holding. And here we have two things. We have synchronized workload and non-synchronized workload. Synchronized workload is the same thing as normal workload with the clock, and non-synchronized is without a clock. So if you see the diagram over here, it shows an example for model assuming release jitter at a single partition. So here is basically where we show the jitter that is being released over here. The horizontal axis represents the time. Down pointing arrow, that is this, is the down pointing arrow shows the represents the arrival of the workload associated with each flow, while up arrow, which is over here, represents the release times of each task shaded by this. Now we have different processors which are present to this. One is the single processor. The single processor is basically each task is assigned to a given partition. All the tasks from E to E flow may belong to the different partitions, and each task may execute within any windows assigned to its partition whenever it is ready, and contents with other tasks in the same partition according to the scheduling policy. In distributed systems, each processor has its own table of partition windows, which is unlike that, which is an advantage obviously. The partition window of the group of the process may be synchronized. This is basically done by a clock. We can have jitter, which is a problem in most of the systems which do not have clocks. And the E2E flow process from one process to another, processes belonging to other different groups do not have the table synchronized because of the absence of clock. Now I'll conclude my video and hand it over to my next teammate.
So hello everyone, I'm going to explain the response time analysis. So response time analysis technology for guaranteeing the timing requirements of a real-time task. So it has two techniques. One is holistic analysis, and the second one is offset based analysis. So holistic analysis improves the RTA into multiprocessor and distributed systems, whereas the offset based analysis it improves the business sum of holistic analysis by taking the two independent and which has same end-to-end flow by choosing the offset. Okay, let's move on partition based scheduling. So we know what is partition. Partition is nothing but a time frame in which the real-time tasks are going to be executed. So it has many timing windows, a number of timing windows. So then each task is coming under the scheduler. So some fixed priority scheduler. Then so to model a partition on which the given task may execute or may not be executed. So for each partition we make a separate analysis. For each analysis we create a end-to-end flow, which is also called the unavailability flow, that is the TU of n. So then for partition PK, this flow is NWK plus 1 of partition windows. Then the JUK of j equal to 0, that means the jitter is 0. Then BUK of j equal to 0, that means best case analysis, which is same as the worst case analysis. So then move on analysis with dynamic offsets. So we know that the response time of one task is equal to the release time of another task. So the time offset will vary for minimum offset to maximum offset. So the minimum offset pi ij mean equal to rij power b minus 1, and the maximum offset pi ij max equal to rij minus 1. Here r is the response time of I and j time frame. Then we can model the case in which the offsets may vary as special case of a system with static offsets. So the static offset pi ij is given by the will be the maximum of pi ij minimum and pi ij of the current frame. So then then we add the jitter to the maximum special time frame. Analysis with dynamic offsets. So we know that the response time of one task is equal to the release time of another task. So the time offset will vary for minimum offset to maximum offset. So the minimum offset pi ij mean equal to rij power b minus 1, and the maximum offset pi ij max equal to or ij minus 1. Here r is the response time of I and jth time frame. Then we can model the case in which the offsets may vary as special case of a system with static offsets. So the static offset pi ij is given by the will be the maximum of pi ij minimum and pi ij of the current frame. So then we add the jitter to the maximum special time frame. So we call higher priority task TAB in the set of task T. So which should be greater than or equal to the current task Tij. So then the analysis is done through the fixed point iteration, trying to find the completion time of every task. So WABCD of P is given by P of CAB plus BAB. Then we create a vector which is I of 0, which is equal to 0. So then the ZI value for end-to-end flow Ti is in the current execution of the busy period. So which is given by ZI of n equal to WABCD of I minus the vector II. So it is given by I of n plus 1 equal to the maximum of IIK, then tau AB and ZI. So WABCD of P it is given by BAB plus P minus P naught of ABC plus 1 into CAB plus IAC into tau AB. So IUD of tau AB equal to summation of for all I we need to calculate I power n plus 1. Then we kept the P naught as a lower number job as for TAB. So IIK of TAB comma ZI, which is equal to W bar IK minus ZI power n. Then for the m plus 1th value, it is calculated as calculated from the previous value. So the W bar IK equal to ZI. Then W bar IK of m plus 1 equal to ZI the previous value is Z1 of n. So when the critical instance coincides with the release of the task, so Wik of TAB comma T equal to summation for all ij. We need to floor the value of Jij plus delta of j comma k by Tia. So plus T minus delta of I comma j by Ti. So the critical instant created with Tij. So delta ijk equal to Ti minus pi ik plus jik minus pi ij into mod. Then we have to calculate the mod value with Ti. Then the length of busy period L of ABCD is given by B plus AB plus flow function of Wik comma TAB comma T plus summation of for all I. We need to calculate I power n plus 1. So now we have the length of the busy period. So now we have to calculate the maximum job number Pi. So PL of ABCD is equal to flow function of L ABCD minus delta ABC by TA. So then we have to calculate the global worst case response time, which is R ABCD of P equal to W ABCD minus delta ABC minus 1 into TA plus pi AB. Then we need to take a worst of all response times, which is RAB equal to max of all the response times RABCD of P.
Let's continue with the analysis techniques in partition systems. Moving on to offset-based analysis with synchronized and non-synchronized tasks. We have synchronized tasks here, which are in addition to the non-synchronized tasks, and hence their period must be synchronized with the major frame. So the period in this case is restricted to be an integral multiple or an exact divisor of the major frame. And the first period inside this major frame is assumed to start at a time phi I called the phase, which is relative to the start of the major frame. And in this case, since the tasks are synchronized with the major frame, and therefore along with the unavailability flow, in order to apply the response time analysis, we need to integrate them with the end-to-end flows. And this together is called the synchronous flow. And there is always one synchronous flow per partition. The period of the synchronous flow is defined as the LCM of the periods of the synchronous tasks and their corresponding periods of the unavailability flows. So each task as well as the unavailability flow in this scenario can be replicated as many times in order to fill all the activations in this period for the synchronous flow. And coming to the offset analysis in this case, each synchronous task has an offset of phi I plus phi ij. Phi I is this phase and phi ij is the offset for each of the synchronous tasks tau ij. And there is priority preservation also here, that is every task here maintains its priority, the original priority. That is, even the unavailability flow tasks, they continue to have the highest priority in the partition. So now let's proceed to construct a synchronous flow. Well, this is the legend here. Partitions denoted by the blue box. Task 1 is green, task 2 is the shaded box, and unavailability flow is the brown box. So here we have a partition window with the major frame of 60. So since the tasks are synchronized with this, the period of the synchronous flow must also be 60. And there are two tasks here, task 1 and task 2. Task 1 having a period of 30, an offset of 0. Task 2 also having an offset of 0 but a period of 60. And look at it, task 1 has a phase of 1 and task 2 has a phase of 42, 2 units from 40. So the corresponding unavailability flow is shown here in this image. This is the inverse of the partitions. And synchronous flow, the combinations of the unavailability flows and the tasks is shown as shown here. The unavailability flows and the corresponding tasks. So we need to analyze all the tasks here in this scenario, synchronous and non-synchronous tasks. So all the instances of the task also have to be analyzed. So for the two tasks here, for task 1, we have two instances. Both these instances need to be included in the response time analysis. Now let's go to the next type of analysis called the best case analysis. So best case basically means that we consider the best case scenario of having the least response time and the execution time of the task is the shortest. So we have something called release jitter here, which exerts a lot of influence in the response time, which we already know. And we must realize that one of the tasks in the end-to-end flow, each task activates its subsequent task, and hence the output jitter of the originating task becomes the release jitter of the next task, which is basically the second point here. And in order to calculate this output jitter, we need to calculate something called the best case response time. And this best case response time calculation could be a little tricky, and in the cases where it's very difficult to find these, we could go with calculating a lower bound. It's 0, but however, we can also use a larger lower value bound, but this will just result in the worst case analysis yielding a tighter value. That's it. So we can go with a simple lower bound value, which can also be calculated. And one of the ideas proposed for the best case analysis was to do it in a single process system using fixed priorities for all tasks, which was proposed by Redel and Sanfordson in their research paper. This is where we assume a certain final time when the work is finished, and we travel backwards from there in time to reconstruct this scenario or the situation which leads to the best case. So the simpler way for calculating such a lower bound for calculating the best case response time would be to consider that there are no contention from all the other tasks, and that the task executes with its best case execution time smoothly, with no contentions among the tasks. So CIJB is the best case execution time. So response time will be nothing but that best case execution time from the starting of the process execution. So now let's move on to the next topic, which is the TTP protocols, time trigger protocols, which are a set of protocols based on the time division multiple axis. And so moving on, let's first look at this image of the TTP network system, where we have a cluster cycle and we have TDMA rounds, time division multiple axis rounds. 4 rounds you see here, and each round we can see there's a slot A. And there are other slots too, but however in this case let's concern ourselves with slot A first. There are a lot of messages, M1 to M2, M3, M4, M1 to M5. So all these messages are given to the slot A, as you can see. So the TTP cycle, this whole setup is called the TTP cycle. And the set of nodes which are connected to a TTP network is known as the cluster. Every node, set of nodes, every set of nodes is called a cluster. And this single PDMA round is one basic unit of communication. So we have 4 units of communication happening in this one cluster cycle. So let's look at what a cluster cycle is. A cluster cycle is a recurring sequence of PDMA rounds, as you can see here from the image clearly, and it is equal to that of an MAF. This is because the sequence of PDMA rounds is where the different frames can be sent by each node in the system, and therefore this is the total period for which the transmission takes place, and hence this is called as a cycle, and it's also equivalent to that of the major frame, since all the frames are being transmitted within this cycle of frame, and hence the cluster cycle is equivalent to the major frame. And this frame can vary from 1 to 240 bytes depending on the situation in which we use this. The application determines the size of the frame, and this method also has certain advantages since that it provides for mode changes. That is, if it has multiple cycles, cluster cycles, it can switch between them, and also provides global synchronization mechanism for the clocks of the various clustering nodes. That is, as we have already described in the task model, there is something called macro tick, which is the granularity of the TTP network time, and this basically determines the precision of the global clock. And using this synchronization for all the nodes, global synchronization can also be achieved. And what we have here is the equivalent partition windows for the system. So the partitioned real-time partitioned distributed system comes into place where for each single PDMA round we have a corresponding partition, the equivalent partition. And since only slot A is concerned, we have slot A for every single PDMA round, and each slot corresponds to slot A, and every slot A corresponding to a round corresponds to a certain partition window in the distributed system. However, this method is limited by 3 assumptions. First assumption is that the messages need to be ready at the start of their slot. So say a message comes after the start of the slot, then this cannot be sent even if there is time available in its partition. So this is the same as if the message came after the entire slot duration. So it is scheduled as if it is arrived at the end of the slot, and hence this has to be treated as an additional input jitter, and hence the additional input jitter, which is equal to the entire slot duration, is added to the next every non-synchronized message. And the messages are also not sent if there is not enough space in the slot. So here we assume that the messages are only sent when they are scheduled, because we consider that their worst case and their best case lengths are the same, and that's essentially because the messages are not fragmented into packets by the TTP network itself. So hence the message has to be sent as a node with a fixed length. It has to be sent as a node. It cannot be fragmented and sent in pieces. And then since we consider that the worst case and best case lengths are the same, we have a certain allocated space for them, and it's all used up, and there is no extra space left for sending any partial messages. That's the second point. And the third is that the messages are non-preemptible. Our response time analysis allows us to go with preemptible cases, preemptible messages. It accounts for it. However, in TTP protocol, there cannot be non-preemptible. There cannot be preemptible messages. It's only non-preemptible, and hence we can implement a message queue by using priorities or simple first in first out queue. And first in first out queue, we consider that all the messages have same priority, but we rank them according to their arrival times. And in this case, for the same priority case in FIFO, blocking which is caused by the non-preemptible scenarios is calculated as something called the preemption time. It's basically like when a set of tasks, a new task comes. So in order for that to execute, all the previous tasks have to execute. So only when all the previous messages are sent, this task is sent. So we calculate that entire time for the previous messages as the preemption time for this newly arriving message. So basically there isn't any actual preemption happening, but we consider this time for the previous message to execute or to be sent as the preemption time. So this is similar to assuming that the messages are actually preempted. That's it. Thank you.
So my teammates probably explained what response time analysis in hierarchically scheduled time partition distributed systems is. Now we are going to look at two particular case studies for this particular example. So the first case study we'll be looking at is the SCADA system with a single processor architecture. Now it is basically a data acquisition system in which the readings are collected from a temperature sensor and then they're stored in an internal data structure, and then they're displayed on a particular screen which compiles all the values from this internal data structure. So now this system is divided into three partitions. Now remember, it's a single process architecture, but it's divided into three partitions. So now the first partition, which contains majority of the system, is created by a single manufacturer. So they are put into one partition, and the other two partitions are basically input and output partitions, which are created by multiple different manufacturers. So there are functional requirements for this system too. The first functional requirement is that the temperature must be from minus 20 degrees Celsius to around plus 80 degrees Celsius. That is, the readings from the temperature sensor must be around this range. The second one, the average temperature along with the timestamp must be displayed on the screen periodically. So there's a screen which connects, which I've already mentioned, that connects and shows the output of the particular sensors which is compiled. Now the third function requirement is when the letter C is pressed, it displays all values since the latest average value that was displayed. So this C is a check operation which basically displays the last average value which was displayed, and from that time to the current time all the values which have been processed. So the next is the timing requirement. The timing requirement is, first one, the temperature must be sampled every 100 milliseconds. So every 100 milliseconds you need to have new temperature. The C operation, that is the check operation, must be completed immediately within 50 milliseconds of the operation being invoked, and the partition windows must have 1 millisecond of granularity. So this is basically the SCADA system with single process architecture. Now this is the architecture diagram. Now here the E to E, we assume that the periodic E to E flows are synchronized with the partition windows, and the keyboard event, which is shown here, are not synchronized. So for this purpose of calculating the partition windows, we use a polling design for the check procedure flow, which is, we are checking check procedure here. So now this procedure flow has a period of 20 milliseconds and a deadline of 30 milliseconds. So now the accurate partitions, how we're dividing the partitions, is shown here. Now the sensor reads acquired value, there's a sensor gets a value and then it reads it, and then the display basically gets the display text and it puts it on the screen. So there is the delay is mentioned and the period is also mentioned. Now the check procedure, which I've mentioned, which has a period of 20 milliseconds and a deadline of 30, because total of 50. So now the keyboard check pressed, when check is done, it should complete within that 50 milliseconds, the check operation. So that's what this is showing. So now we'll move on to the partition assignment. Now there are three partitions, like I already said. The sensor, which is the majority, will be consisted in one partition. Now the rest of the two partitions, P2 and P3, they have multiple components in its partitions. So in this case, what we do is we have to assign priority for each of them, because, well, you can't have the same priority for each and every operation. So all of this will have a different priority. So for the priority assignment, what we're doing here is they're assigned low and high priorities based on, well, their precedence, and according to a particular assignment mechanism called the deadline monotonic assignment. We haven't learned about that right now, but it's an assignment technique for priority assignment in which it assigns in the partition what priority should have, which component should have what priority. So that is basically what is happening here. We are assigning the priority. So if you see the sensor, read, display, check, keyboard, screen, put record, and screen put line, they are all operations and tasks that need to be performed. So my colleagues would have explained the partitions and all the functions and what it does. So sensors, read, display, it's all present in the architecture in this diagram. So now so there are multiple cases which you can actually analyze, but to save time I've put only one simple case for this. Now there are three partitions. In this case it's a synchronized polling and there are no offsets at all. So what you can analyze from this is, we can see that we are able to guarantee maximum sampling jitter requirement for this particular sensor task. So now even in the other cases, the maximum sampling jitter requirement is satisfied, and if we have the one with the particular offsets, we can also see some more improvements. So that is currently not being explained in this particular presentation to keep it short. So this was the first case study. The second case study is the trajectory corrector system. Now this system, there are multiple components of the system. First of all is the FCM, which is a flight control module, ADC, air data computer, GPU, global positioning unit, everybody knows that, ACEI and IS2, actuator control electronics, and INS, inertial navigation system, DCU, data concentrator unit. Now all of these components are part of this trajectory corrector system. Basically you're correcting a trajectory of something. So this is the architecture in which we are using. There are multiple CPUs. Remember, this is a different distributed system. The first one was a single processor. Now the second one is a distributed system. So here you see all the components which I've mentioned, and they communicate through a shared bus. There are various communication methods which we already learned before, so we are optimizing it that way. Now we have particular assumptions for this network because it's a TTP network. So the assumptions for that network, based on the TTP which is explained by my colleague, is the speed of the network must be 4 megabits per second, the interframe gap must be 25 microseconds, the minimum slot size must be 50 microseconds, and the macro tick size should be 4 seconds. These are some basic assumptions we're taking. And for the requirements, there are some particular timing requirements for each and every component. As mentioned by my colleagues earlier, there are timing requirements, and these timing requirements are then partitioned into windows. Now if you see here, we have INS, FM, and all of these have some timing requirements. All these variables have been explained earlier. And then the partition windows, basically we have CPU1, CPU2, CPU3. There are 3 different partitions. Now each partition will have their own components, and then so before I move on, I will talk about. Now the E2E flows take place in the system. This is the figure that's shown for the E2E system, E2E, which is again end-to-end communication. Now the messages that arrive at the destination are stored in a buffer first, and then are read asynchronously by the destination task. Except for FCM1 and FCM2, which they cause the execution of task ACE and ACE2. So except for them, everything else, the messages at the destination are first arrived at the buffer, they're stored first, and then after that they're asynchronously read by the destination. Okay, now coming back to the timing requirements, we see that these are the timing requirements for this, and these are the particular partition windows that was performed in this paper. So now each and every task has some message ID, and the messages have some origins and the size of bytes and all that. So the greatest common divisor of the periods define the maximum TDMA round that we need to use, and since each node is allowed to send only one slot in each round, we have the maximum TDMA round. So the least common multiples, that is the LCM, defines the cluster cycle. So in this case we have a cycle of 100 milliseconds and a TDMA round of 25 milliseconds, because the maximum LCM is 100 and the TDMA will be 25. So each message based on the partition systems and the timing requirements are given a particular slot. Now these slots correspond to how much time each message takes and how much time each message actually executes for. Assuming that the CPUs and the network schedules are synchronized, we can run each task in a separate partition. So now in the end we have this result. We can see that all the timing requirements are met, and we have a small jitter value which is 0.1 due to the synchronized nature of implementation, because here we don't have all the processes in one particular system, so it's a distributed system, so there will be a little bit of jitter. So that is all there in this system. The system has to manage with this jitter, and it's optimized to manage in that way. So in this presentation we've discussed the entire paper written by the authors, and we've analyzed methods that apply offset based response time techniques to analyze real-time systems based on hierarchical scheduling and time partition scheduling as a base policy, and fixed priority secondary schedulers in each partition. The task model includes both synchronized and non-synchronized tasks. The methods developed are applicable to both the single processors, as we saw in the case study, and also the multiple processors, that is the distributed processors, which we've seen in the second case study. So using these techniques we can actually optimize the way we communicate with the processors, and we share memory and all that, and we are basically combining everything from different manufacturers and making a seamless transition, so that we have least amount of jitter time and there will be least amount of speed reduction. Thank you.